You see here, this is where we think the universe was smaller, right? This is when the Big Bang happened. This is at the Big Bang itself. We think the entire universe was smaller, hotter, and denser, right? Imagine the entire universe compacted to one volume, right? That's what the universe was like. We can see this with CMB radiation. So, as the universe expanded, what happened was there was this inflationary energy that pulled and stretched space and time itself. No, don't think of it as a sphere. That's the problem, right? We can't imagine. It's hard to fathom the Big Bang because we tend to think of things within space. But the Big Bang happened everywhere. The Big Bang happened where you're standing. The Big Bang happened everywhere. The entire universe was condensed into this one area, and then it inflated. Not one area, one volume. And from there, what happened was the universe was so hot that gravity, the forces of nature, were all combined into one superforce. But as the universe expanded, it cooled down, it allowed those forces to separate. Nope, it wasn't one single point. The universe did not expand in one single point. It's expanding in every point. Every point of the universe is expanding. But as the universe cooled down, it expanded. As it cooled down, in other words, the volume got larger, right? And this allowed for the forces of nature to separate. And this allowed matter to form. Gas clouds were prominent in the early universe. And these large gas clouds condensed into galaxies. And then stars, right? Stars formed, the first stars, then the first galaxies. You have enough stars, you have a galaxy form. And here we are today, 14 billion years later of expansion, right? The universe getting colder and colder. Here we are today. And that's all the Big Bang means. We're not expanding into something. That's a misnomer. We're not expanding into something necessarily. The universe could be all there is, right? The universe might be everything there is. There might be no end to it. But here's a kind of a good picture of what happened here. So, like I said before, as the universe expanded, you got gas clouds, which dominated the universe. Here we have a nebula clouds, right? Gas clouds. But what happens? Gravity tends to want to collapse these gravity clouds into disks. It's called angular momentum, right? They tend to want to collapse into disks, and they start rotating due to angular momentum. And as they grow in momentum, they grow in speed, and a lot of stuff collects in the center, right? A lot of heat, a lot of dust, and gas collects in the center. And if you have enough energy there in the center, you have a star, the beginnings of a first star. So this is the first star, right? It was a ball of plasma. So that's what stars are. Stars are balls of plasma, nothing more. But if you have enough heat, you have something called fusion occur in stars, where you have atoms fused together, become larger atoms. Hydrogen, right? Hydrogen atoms, some of the first elements in the universe. Those fuse together into helium. Helium can fuse to carbon, etc. And they can also produce light. They can also produce light and radiation, and that's what a star is. But you need enough mass for this to happen. If you don't have enough mass, you're just going to die, right? You're going to get cold and die away, fade away. So a star has to have enough mass to burn. This way it sustains itself, and there's an outwards pressure that builds. That's how a star works, outside pressure. But you also have gravity pushing it in, right? So you have this equilibrium occur between outwards pressure and inwards pressure, keeping a star afloat. Then once you have a star, it produces a shock wave, and the shock wave pushes material outwards, right? You still have a disk around it of gas, but it pushes it outwards, and it allows the outer material to become colder. Little rocks precipitate, things like that. Dust, grains, sand, these things precipitate from this material. And what happens is you have the first planets. Right? So just imagine all the material floating around this thing, and all these little rocks, right? They clump together. And in space, it's very easy for things to clump together because there's something called cold welding. There's no air in the way. So you have an easier way of making larger materials. And this is called a planetesimal, where you have a very hot rock, but it gets larger and larger as it grows in gravity. It gets larger and larger and becomes larger planets, right? Spherical in shape because gravity wants to push it downwards in all directions. So you have a planet form like the Earth. Now, about 4.5 billion years ago, the Earth was much warmer than it is today. In fact, the Earth was much like a molten rock. It was molten. It was liquidy. The Earth was liquidy because it was so hot, right? The iron. Today we have like metal, for example. Metal is solid because the Earth is cold. But in the past, the Earth was much more warmer. Hence, even iron was liquid. Even iron itself was melted and became liquid, like water. So what this allowed was the lighter material to stay on top, but the denser material, because of its density, right, like iron and the heavier elements, they sank to this core, and they developed the core of the Earth. And this allowed the mantle, the core to form, and the layer on top of it become a crust. The layer on top of it got colder over time and developed a crust. But you still had a very warm climate for the first billion years of Earth's history. A lot of volcanic activity, a lot of gases, but still being bombarded by asteroids from space. And over time, a lot of this debris and stuff collected. A lot of these asteroids in the solar system contain water ice, right? Water forms in space. Water formed in space, and this allowed water to make its way into rocks around the planetary disk. And as these rocks bombard the Earth, they hit the Earth, they strike it, they turn to gas, right? They immediately turn to gas, but they stay in the atmosphere because of Earth's gravity. It holds it in the atmosphere. And as the Earth cooled down, it was allowed to become water. It precipitated into water as the Earth got colder. And this allowed for oceans, the first oceans to form, right? You have lots of rain in the early Earth's history. Lots of rain, lots of lakes, lots of ponds, and lots of oceans. This also allowed it to be salty. But you also have stuff mixing with the soils, mixing with the dirt, making salt that way. But about 3.5 billion years ago, as soon as the Earth got a little bit colder, life began. Life began in the oceans, near hydrothermal vents. For life, you need energy. You need energy for life. You need certain ingredients like amino acids, lipids, phosphates. And these amino acids are formed in the Earth's atmosphere. We can make the building blocks of life in labs. We can make them. We know how they're formed. They're formed in the Earth's atmosphere. And over time, these molecules, because they're carbon-based, they connect together. They link together in chains and become more complex over time. And that's how the first life arose. The first life arose in the oceans, in the lakes and ponds of the early Earth. Then you have an atmosphere. Plate tectonics occurs. So the plates on top of the Earth, because of the mantle was liquidy, the crust was able to move upon it, and became plate tectonics. This is what plate tectonics is. This is why we have mountains. This is why we have earthquakes and volcanoes, because you have dips and valleys in the crust, and the plates can smash together and become mountains like this. Imagine two plates colliding. That's a mountain. Imagine plate sinking, right? Sinking. Well, that's a ridge. There's a word typically where earthquakes happen during those times. Now, the first living things were cyanobacteria, which produced oxygen. There was no oxygen in the early Earth's history. There was very little oxygen. But in order, as cyanobacteria use the CO2, nitrogen in the atmosphere, they actually produced oxygen. It's a byproduct of CO2 and photosynthesis, for example. And that's why the Earth was full of this stuff, and it produced lots of oxygen, and it went to the atmosphere. And it was able to, produce other living things. Other living things are able to use this oxygen and become more complex. Then for the first 3 billion years of Earth, life was in the oceans. Life existed in the oceans. It's bacteria, and then insect-like species, worm-like species, and then fish-like species, and then trilobites about 1 billion years ago, 1.5, 2 billion years ago. Fish are relatively new, about 600 million years ago. Some of these fish developed certain protolimbs that enabled them to walk on land for a little bit. Not fully, but they could stay on land. The first trees emerged about 300, 400 million years ago. 400 million years ago, the first trees. And the first fish, the first amphibious creatures, making their way slowly onto land. And over time, they went more and more onto land and their limbs developed even larger and became larger limbs. Eventually, arms and legs, like reptiles have. Fish didn't just grow legs. That's not what we think. That's not what happened. It's not that the fish automatically changed into a reptile, right? It was a series of many generations in which protolimbs, very small limbs, became larger and larger because of the generational mutations that occurred. After the reptiles, we have dinosaurs, right? Dinosaurs emerged around the same time as reptiles, and you have the dinosaurs like T-Rexes, right? Some of the biggest predators, herbivores. Dinosaurs existed all over the continents. Almost every continent was full of dinosaurs, even Antarctica. Even Antarctica, which was at the time about 70, 80 million years ago, it was not icy. It was fairly mild in temperature. And it was greenery. There was greenery in Antarctica. There were lakes, and dinosaurs lived there. And as time went on, the plates shifted. This is how plates shift over time, over many millions of years. It doesn't take a day; it takes millions of years. But again, 60 million years ago, what you have is the asteroid impact, right? And what that happened was a lot of the debris went into space. A lot of dust surrounded the Earth. It blocked the sun. Right? The impact destroyed a lot of the dinosaurs immediately. But dust from the impact covered the rest of the planet, and this stopped a lot of the sunlight from reaching the surface. But 75% of the dinosaurs died. 75% of all life died in that extinction event. And we can see this in the geological strata. We can see a layer of iridium, which is linked to the impact all across the world. But from the animals that did survive, those were the mammals. Mammals survived. At the time, they were small. They were kind of like marsupial creatures, like squirrels. But the mammals became different, right? Over many millions of years, they became more complex. From consuls to first apes, they walked on fours. They lived in trees, right? But then over time, we shifted towards the grasslands. We started walking upright, right? Because the ones who could walk further, they were able to survive better. And here's Homo habilis, some of the first humans. And this is habilis right here. He started walking, developing fire. He developed tools, right? And these enabled us to live almost anywhere, right? We started developing tools and finding new places for habitat to live and to find food and water. And this allowed our ancestors to survive in Europe, in Asia, and migrate across the earth, migrate across the surface of the planet. And this is about 20,000 years ago, right? We lived together. Neanderthals, this is during the Ice Age. We fought off mammoths. We found anything we could to survive. We also lived in the Arctic, very cold climates of the Arctic. But about 10,000 years ago, we began to develop agriculture. We developed to not just forage for food, but now the food we made for ourselves. We were able to settle down and live in civilizations, live in cities where we can grow our own food. And this changed us forever, because now we don't have to spend as much time looking for food. Now we can grow it, and we can have people collectively making it for other people, right? In an economy, right? Then you have people focusing on developing better tools for the economy, right? Engines to make things produce faster. The Industrial Revolution occurred. Cars, travel, all these things changed us a couple hundred years ago. And now here we are today, where we have societies that are able to, do many amazing things, go to the moon. We can, change the world. Now we have a lot of potential now. We have a lot of smart people on this planet, a lot of scientists who are doing great work, giving us medicine, right? Giving us cures to diseases that just a couple hundred years ago would have been crazy to imagine. Giving us phones, technology, internet, right? This allows us to communicate faster. Right? But yes, we're also ruining it. We're also destroying other species around us. So it's a very interesting time we live in, right? One where we have lots of power, but lots of ignorance, which is a bad thing. So here's some of the first apes. So let's take a look at some of the first apes. People ask about, well, where do we come from? Well, these are the ancestors that we had. This is about 4 million years ago in Africa. During that time, there was climatic changes happening in Africa. Our ancestors lived in the trees, right? They lived in the trees. And these are Australopithecus ramidus species. You can see their feet were not like ours. They were graspable, right? They can grasp with their feet. But they could also walk upright to some degree. And they would look at predators from the trees. They would hide, and they would scavenge for food when they left the trees. See? Predators. You got predators. You have food. There is a reason why they had to survive, and they had to develop ways to survive. And this happened generation after generation. Some of our first ancestors left the trees, right? Slowly but surely walked out of the trees, looking for food. And this is what made us human. This is what made us human. The first time we left the trees and started migrating across Africa. Look, we're finding food. And these were very intelligent humans. These weren't humans necessarily, but these were our ape ancestors. Mm-hmm. They were very, very smart. They knew how to find food. They're also very social animals. They lived together. They were monogamous as well. They had families. They lived together in families, and they were able to survive because of this. Right? This is where morality begins. This is where our morality comes from, right? Families working together for the common good, for the common survival. Next, we have 3 million years ago. Now we're more advanced. Now we're migrating through Africa. Now we left the trees for good. Now we're fully on foot. We're no longer in the trees. These are our human ancestors now. This is Australopithecus afarensis. This is the last ancestor with apes, the last common ancestor, and the first humans on ground. You can see they're very much like us. They can walk upright. They had less fur. They traveled in families. They had tools. Some some got eaten, right? So they had to develop communities to fight together. And here's the Stone Age. Here's Homo habilis, the first humans. These are some of the first humans. Yeah, they're very similar to us. Just a couple million years ago. This is Africa. They became smarter, right? Developed new ways of hunting, new ways of finding food. They lived even together, even more together. Stones. They first developed stones and fires. And this allowed them to become smarter and smarter. This is about 1 million years ago. Okay, now we are even more intelligent. Right? So this process of surviving in Africa changed us forever. It made us human. A lot of, and there were many species of humans too. Many species of humans lived together. Homo sapiens lived together with Neanderthals. There weren't just one type of people. There were multiple types of species of humans. And we made it. In fact, many people today have Neanderthal DNA. You guys are all laughing, but this is a fact. These are facts that you can back up with the evidence. And they developed language, they developed religions, they developed languages. They survived in Europe. Now they're in Europe, right? Now they're in Europe and Asia, and this allowed them to become more genetically diverse. The skin color changed. They lost more hair. They became more like us today. So yeah, that's our history, and that's amazing. And yes, this is all fact. You can go look all this up. We have all these fossils. We have our DNA, which demonstrates this. We have all the evidence you need. Go learn. That's the beauty of science. Anybody can do science. Science is amazing. It's not. It's a fact. This is a fact. This is really what happened. This is how we got here. Right? People ask all the time, "How do we get here?" This is it. Evolution. Millions of years of changes, small changes over time. Now, when it comes to the universe, right, we went over the Big Bang. But here's all that visualized, right? Here's all that visualized. From simple cells to bacteria. Hold on. Right, there we go. So from simple cells to bacteria, more complex cells to worm-like insects, and then fish, amphibians who can walk on land a little bit, then reptiles, and then mammals, and then from mammals, apes to humans. And now we are today. We are a great ape. We're still apes. We are still completely apes. But we are just a little bit smarter. It's not BS. This is a fact. This is a fact. This is really what happened. I know you guys want to laugh because you don't understand it, but this is really how it happened. And but here's a history of our entire universe as a whole. Galaxy formation, nebula clouds, dust clouds, right? They begin to form stars inside of them, like we talked about before. Right? These are star nurseries, where stars are born. In gas clouds, this is where stars are born. This is how our Earth got here. This is how the Earth got there. Bombardment, like we went over, right? The Earth got warmer. Volcanic activity spewed gases, made an atmosphere. Life, the first living things, mitosis, cells, cell division, has proliferated our life. And life is just molecular activity, chemical processes, right? Chemical processes. Every one of us are made of bacteria and cells that make up our body, working together. It's just chemistry. It's a very complex chemical process. And again, first life in oceans. The earth went through changes. More complex living things developed, multicellular life, fish, land animals, dinosaurs, trees, reptiles, apes, and humans. Right, here we are today. So yeah, that's quite amazing who we are and what we are. It's all beautifully complex. Yeah, that was a lot of information. But any questions you guys have? No, these are not stories. These are facts. We can observe everything we see. Everything here we observe with telescopes. We observe the fossil record. That's what science is all about. Science is about learning what really happens, uncovering the truth of reality. That's what science does. And it really happens, and it really works. Why don't you talk about the size of Africa? What do you mean? Can you show us how the Earth was made? I did before. But you can go on my YouTube, and I have more information on my YouTube about this. Why are you so sure? Were you there? We don't have to be there to know what happened, right? We have the fossil record. We have our DNA, which leaves traces. Right? We have the fossil record to leave traces of this. Who discovered oxygen? People, the 1700s did. They discovered it. Why does everything need evidence? Because if you don't have evidence, you don't have facts. You need data to support your facts, to support the truth. But yeah, these are real images of space. Right? These are real images of space, remarkable images of space. Here's Jupiter. Here's Jupiter right there. And you can see that Jupiter has this red spot. That red spot is a gigantic storm. On Jupiter, the storms are big because there's no friction. There's no land on Jupiter. It's just a big gas giant, right? Fully gas. And this can make storms and winds hundreds of miles an hour, 600, even 700 mile per hour winds. Imagine winds the speed of sound traveling through Jupiter. An amazing planet. Here's some more nebulas. Here is galaxy NGC 2525. And each one of these dots is a star, right? And galaxies are made of hundreds of billions of stars. Hundreds of billions of stars in each galaxy. And here's a bunch of galaxies. Look at how many things exist in the universe. Right? Think of how many stars. Think of how many stars there are. It's amazing. Think of all the stars and all the galaxies out there. More gas clouds. These are real gas clouds that we can see with telescopes. These are where stars are born. This is how stars are born, in these gas clouds, right? Certain areas, they collapse because of gravity, and they can make dense spots where stars form. And more galaxies. Some galaxies collide with each other. Galaxies are moving through the cosmos as well. And they can collide, become larger galaxies, larger black holes. Here's Saturn, a real picture of Saturn. Saturn's rings are made of, look at this, quite an amazing planet. It's a big gas giant, again, full of gas like Jupiter, a little bit smaller than Jupiter, but still. But it has a unique set of rings around it. And these rings are formed out of icy rocks, right? Rocky material, little ice. Some rocks can be as big as mountains around Jupiter, around Saturn. And Saturn also has about 60 moons orbiting around it. 60 moons, right? Moons, some of which are bigger than our moon, right? So there's a lot of things orbiting around Saturn because it has a lot of gravity. But these rings are very new. In fact, Saturn's rings are always being formed and destroyed all the time because it's very icy there. An ice can build. Saturn stuff can build up there, out there from other material. Here's a Crab Nebula. These are nebula clouds. These are typically supernova explosions, the remnants of a supernova explosion. Right? Stars can explode if they get big enough. If stars get big enough, they explode. What happens is a star runs out of fuel. Right? It runs out of energy. It can no longer produce energy because the atoms are too big. Fusion occurs when a star is big enough to has enough mass to fuse certain elements together. But if a star is too big, and if those elements are too big to fuse together, because it takes more energy to do so, if those elements are too big, it stops producing energy. And at that point, gravity takes over, right? So as a star runs out of fuel, gravity collapses it. And it collapses so quickly that it crushes under its own weight. And then it implodes. It explodes out into space. And all that gas and dust from the star, all the plasma, all those elements, right? All those elements of helium, nitrogen, oxygen, nickel, iron, all these elements that make up you and me, calcium, right? The calcium in your teeth and your bones, right? The carbon in your skin. All those elements that make up you come from these stars that exploded. That's what this gas is, right? All this gas is stuff like you're made of, the same elements that you're made of, the same matter that you're made of. So when we say you're star stuff, that's what we mean. We are star stuff. We come from space and the stars. Here's more galaxies. Look at these beautiful galaxies, these beautiful structures. Again, they're collapsed because of gravity. Gravity likes to collapse things together, and because of angular momentum, they want to spin. And the spinning allows it to become a very, very large object. A very flat object, very large object. More beautiful galaxies. There are trillions of galaxies out there. Trillions of galaxies. Trillions. That's as far as we can see. Here's a beautiful nebula. So this is how our sun will die. This is how our sun will die. If you notice, there's a little star in there, a little dot right there, right? That's a star that died. And what happened was, when our sun dies, it will run out of fuel as well, but it won't explode. It doesn't have enough gravity to explode. What will happen is, it will turn into a white dwarf. It'll collapse. The core will remain, but slowly and surely, the gases, the plasma that surrounds the core will be stripped away and sent into space, slowly producing this ringy structure, right? So what you're seeing here, again, is heated gas, plasma, that is emitted from the star. Much more silent, but not as nasty as a supernova, but still a very amazing event. Here are two galaxies colliding, which is amazing to understand. Two galaxies colliding. Again, these are real images, guys. These are real images. We really can see these things. This is remarkable, right? Think of all the ancestors we talked about before. Think of all those ancestors that came before us. They never saw what we can. They never had the opportunity to look through a telescope and see these magnificent things. Think of how remarkable today's world is. Here's Mars. If you notice, Mars has these little white things on the poles. Those are ice caps. Mars is very much like the Earth. Mars has an ice cap too. And they actually have lots of water in them too. Water ice and also CO2 ice. So we think that one time in the past, Mars was full of water. Oceans of water. Lakes and rivers. Imagine that on Mars. There could be life on Mars. There could have been life on Mars sometime in the past. Today it's a dry, bare bones planet. It's very cold on Mars. But in the past it could have been much warmer. Here is Uranus. Uranus spins this way. It spins lopsided. And we think it's because of a asteroid impact or a planetary impact in its early history. That's why it made it look like that. But Uranus also has rings. In fact, every gas giant has rings to a degree. But Uranus has smaller rings. It's not as visible as Saturn's. Here's a clusters of stars, right? Think of all these stars. How many planets could there be around these stars? I mean, there could be so many types of life forms out there. No, these are not CGI. These are real images. These are real images. We've really seen these things with telescopes, and that's remarkable. You can do it as well. If you're that skeptical, you can go look at these things with your own telescope. Well, not some of these things. You need a space telescope for that. But you can still see galaxies with the telescope. You can still see all these planets. You can go see it for yourself. These magnificent structures. Amazing how the universe operates. But yeah, we have the fossils. And again, how evolution works is, again, when we say we come from monkeys, we don't mean we morphed from a monkey to a person. What we mean is we share ancestry with monkeys. Evolution works like a tree. Evolution works like a tree. Imagine a tree with branches. Every branch, you have a new species, right? So you can fork, right? Imagine like a river that forks in two, right? It goes two separate ways. The same with evolution. You can have a population of animals here. They split in two. One goes this way, the other goes this way. This one evolved separately from this. Right? And that's how evolution works. And these population continues going, and they split even further. They split again. Population splits again, and they turn into gorillas. And this one keeps going. And this splits again. This goes this way. This population goes this way. It turns into bonobos and chimps. And this one became humans, right? So again, if you trace back all of the branches of the tree of life, you can find that we all share that one common ancestor about 13 million years ago. The first apes, right? That's evolution. It doesn't happen in one day. It takes many generations. But you can see that that's how life works. It's a tree. It's a tree of speciation. All right, that was a lot of information. Any questions? Evolution takes a long time. Exactly. Evolution takes a long time. Think of evolution. Think of small changes over long periods of time. Small changes can build up to become big things over time, right? Imagine building a building, right? You put the foundation first, the next floor, right? Floor by floor, you get a larger structure at the end, right? So small changes can make big changes at the end. That's how evolution works. But changes happen all the time, right? The changes happen in your DNA all the time. Your DNA is always changing because that's what it does, right? That's how chemistry works. Mutations can affect it. There's reasons why there's mutations, right? There's errors. Errors can be had in your DNA and it can change. That's how we change. How was the universe made? Well, we don't know if the universe was made. The universe could be everything there is. All that is, all that ever was, and all that ever will be. It could be everything. Maybe there is no outside the universe. Maybe the universe is everything there is. So it could have always been here this way. Will the universe ever end? Yeah, it seems to be that the universe will continue expanding forever. But ending is a weird word. It's an interesting word. Science lives are boring. It's boring if you don't understand what I'm saying. If you took the time to understand this, if you took the time to understand how the world works around you, It's the most amazing thing. It's the least boring thing in the world. If you just understood what these structures are, right? If you just understood what this was, what these things are, the amount of information out there is way more than I can even ever be satisfied with. Can we do debates? Yeah, I know you want debates, and I'll do them, but sometimes you have to learn, right? If you can't debate if you don't know what you're debating about. You have to learn some science. It'll change the way you see things, right? Because from this perspective, right, we can take a look at things like we sent a spacecraft out about in the 1980s. We sent a spacecraft out into space, and it had a camera on it, and it's called the Voyager spacecraft. And right now, it's outside of the solar system. Right now, it's very far away from us. But it was lucky enough to look back, right, in its journey through our solar system. It was lucky enough to look back onto the Earth and take a picture. It took a picture of our planet. And it's called the pale blue dot, right? This is an image of the Earth from space. Do you see it? Do you see it? That's it. That's the Earth from space. Right? That's our entire planet from space, right? Look, this is just a fraction of what's out there, but look, it's darkness, it's a void, it's very empty. And there we are, right? Just floating there. This little dot, this one pale blue dot. That's all we got. Everything you know, everybody you love, every person you've ever known lived on that dot right there. Right? And from this perspective, it's a really, really, really crazy way of realizing what we are. It's a different perspective, a cosmic perspective that changes how you see yourself and people. It's not CGI. These are real images. It's not CGI. You guys can say CGI, but how do you know that? You don't know. You don't even know what this is. You don't even know what this is. How can you say it's CGI? Well, everything's CGI except for God. Everything's fake except for your Bible. That's not how this works. Think for a second. Realize that this is a real image. Learn. When you learn more about the world around you, you're going to realize that it's not CGI, right? So just look at that. That's just realize that what we are is not what you think it is. It's different. There's a different way of viewing the world than just, oh, we're the center of it, right? Does that look like the center of the universe to you? Does this look like the main character of the universe? I don't think so. It looks like a nothing. So again, no, it's not CGI. It's real. Just because you don't like it, just because it debunks your belief or it makes your belief challenged, does it mean that it's wrong? It's not CGI. Look it up. Look up Voyager. Look at the Voyager spacecraft. We have the images from the spacecraft. All right. Anything else you guys want to talk about? It's not NASA lying. No, NASA doesn't lie. The only lie is your religion. The only lie is the fact that you think that there's talking donkeys. That's a lie. James Webb Telescope. Yeah, We can take a look at the James Webb. James Webb was a big boy. Yep, Numbers 22 is where it says donkeys can talk in the Bible. Numbers 22. You guys are so skeptical of the science, but you're never skeptical about your Bible. Right? You're so skeptical about the image from a telescope, but you're never skeptical about talking donkeys or virgin births. Come on, that's ridiculous. Learn about the world around you. Learn. Wow, these are real images from the James Webb. This is a galaxy called N51, very massive galaxy. Here's a dying star, a nebula dying star. Beautiful images, amazing. Wow. And if you notice, you'll see in these images that these are all galaxies. Again, each galaxy is here full of hundreds of billions of stars, hundreds of billions of planets in each one. Perhaps just like the Earth. But also, you'll notice that there are stretch marks here, right? These little squiggly lines. And the reason why is because the light from those galaxies are so far away. Some of these galaxies are, billions of light years away. Billions of light years away. These are very far away. But because they're so far away, they're traversing the light. Light travels through space. Right? Light's moving through space. And what happens is gravity is a warping of space. You can't see it directly. I can't see gravity with my eyes, but we know it's there because there's a space and time fabric warping, right? Space and time can warp, it can bend. Mass, if there's mass, there's a black hole, for example, right? Lots of mass, lots of stuff. It can bend space. And as the light moves through space and it passes by that black hole, that gravitational thing, the light itself can bend. The light itself can bend, and this is what we see. This is the result of it. What you see is this little line. That's from the light bending. It's called gravitational lensing, right? Gravity can bend the light. And from the telescope we see, it looks like that. That's remarkable. Because what that means is now we can see that there are things in this picture. There are black holes in this picture. Very large black holes that are stopping the light from being coming straight through. This is something that we've just figured out in the past 50, 60 years, right? Even Einstein himself rejected the notion of gravity waves. He didn't think that would be possible. But we see it. And we see it. That's how powerful science is. It predicts things 100 years before and gets them right. 100 years later, it gets them right. Here's an image of Saturn from the James Webb. Webb makes the first detection of crucial carbon molecule. So this is the Orion Nebula, and what we found is we can take a look at the cloud is under certain frequencies of light, right? Infrared, visible. There's many spectrums of light that we can't see with our eyes, right? Our eyes are very limited. But in the universe, there are different spectrums of light, and what that means is under certain frequencies of light, it interacts with matter differently. So, if we see, for example, this cloud in infrared light, well, we can see deeper into it. We can see deeper into the cloud. We can see now that there are potential molecules in these clouds. Molecules of life, perhaps. Or not of life, but the building blocks of life, right? Amino acids, carbon-based organic molecules, perhaps, in these clouds. right? Like, just imagine that. Understanding that there are molecules of life found in clouds all around the world, in the universe. And that's what the James Webb is able to figure out. Here's a very interesting picture of galaxy formation. So how it works is stars form first, right? The galaxies start to assemble. They look like little bubbles, right? They look like little bubbles. Then the galaxies begin to change the gas around them. The galaxies develop more gravity, right? More gas. There's different gases around them. The areas of gas expand. The universe expands, and this causes the clear universe we see today, right? So in the early universe, the universe was full of lots of gas, ionized gas. Deionized gas that was getting in the way. It was the dark ages of the universe. There was no light passing through. But now what we find is, as the universe expanded, it allowed that light to pass through and reionize. Wow, look at how many stars there are. That's remarkable. Oh, here's Enceladus. Here's a moon in Saturn spewing plumes from one side of it. And this is from the Cassini spacecraft. And what it found is that Enceladus actually has volcanoes. There's volcanoes. Well, not volcanoes. I'm sorry. Hydrothermal vents under the oceans. Let me pull up a. Here's the moon of Saturn. Very amazing moon. If you take a look at it closely, you'll find that it looks like this. It looks really interesting. It has these stripes in it. Right? This is a moon of Saturn. It's about 300 miles wide. It's very small. But it has these little stripes in it, these blue stripes, right? Look how amazing that is. And it kind of resembles ice, right? If you take a look at ice or snow on the Earth, it looks like kind of like that, right? Well, it is. It's ice. It's snow. On Enceladus, its surface is covered in ice, water, ice, and snow. And not only that, but under the ice, we think is an ocean of water, liquid water. In fact, there might be tons of liquid water in Enceladus. Salty water. No, we know there is. We know there's water there. We can measure it by looking at the plumes. That was the thing I was going to get to next, right? When we look at the plumes, here's a perfect. I love this picture. So here's Enceladus. Hold on, let me get back to that. Yes, here we are. So you can see that under the surface, and the ice is 30 miles thick. 30 miles thick of ice. That's a lot of ice, right? But under that ice is a blue ocean, right? Ocean, global ocean. It surrounds the entire planet. Ocean, water. And what we think is that this is where the hydrothermal vents are. They're underneath the oceans. They're in the oceans. And there's the hydrothermal vents are spewing water out of it, right? But there's pressure. There's enough pressure there for them to get that water up to the surface, and then it spews out of these cracks, right? Water spewing out of the cracks of Enceladus, and that's what you see when you look at the plumes, right? When we look at the plumes, we're looking at those cracks right here, right? We're looking at water coming out of the surface, spewing out into space. Water, and we've also found not just water. We've also found the building blocks of life, amino acids. We have found in this gas. We know We know it. In fact, our Cassini satellite probe has spun around, has flown around this moon and taken a sample of it. We have a sample of this plume. We took a sample of it and we realized and we analyzed it spectrometrically, and we found that it has water, methane, some other types of gases, and also amino acids. There's building blocks of life there. So that's amazing. That's remarkable that we found this, right? That on another world, in our own solar system, is an entire ocean, perhaps life, living things under it, living life forms, perhaps bacteria under the surface of Enceladus. And this is a moon, not even a planet. So that's amazing. If this isn't amazing to you, I don't know what is. I don't know what is amazing. This is a stunning fact of reality. To answer some questions now. You seem chill when you're not debating. What about life on Mars? Well, there's no life on Mars today. Mars is very, very cold. Let's take a look at Mars. Yeah, here's the surface of Mars. Here's a real photo of Mars. It's amazing. Because remember, we have rovers on Mars. We have rovers on the surface that are rolling around. And look, there it is. The surface of another planet. That's amazing. Never before have we seen this until a couple of decades ago. And we can see on the surface of Mars there are mountains. In fact, there's volcanoes that are dead now. They're not active volcanoes, but they're past volcanoes. There are also lots of rocks. These rocks are very similar to Earth rocks. Very, very similar. We also know that there's lake beds. The remnants of lake beds on Mars. History of oceans and rivers. Flowing rivers. Yeah. But today again, like today, the Mars is very, very cold. At the poles of Mars, it's around negative 200 degrees Celsius. That's cold. Okay, that's cold enough to freeze CO2, which is a gas in our atmosphere. But it's like dry ice, right? Ever had dry ice in a science lab or at school, right? That's what CO2 ice is. That's CO2 ice in ice form, right? But if you notice, if you have it out too long, it gets gaseous real quick, right? That's because it sublimates. That's what happens when you have the properties of CO2 are that way. Pressure differences as well can do that. But the point is that on Mars, CO2 ice is static. It's there normally, right? It's also underneath the ground and the subsurface below the soil, right? Below the soil here is ice. A lot of ice. Water and CO2 ice under the soil. But there's probably no life. There's probably no life on the surface. Another reason why there's probably no life on the surface is because Mars has very little atmosphere. The atmosphere on Mars is very thin. It has an atmosphere. It's very thin though. CO2 mostly CO2, and that's it really. Maybe a few other gases, but that's it. So Mars is very cold because it has a very thin atmosphere. See, on Earth, our temperatures are very warm because we have a thick atmosphere, relatively speaking. But on Mars, it's very thin. More heat can escape. So life probably doesn't exist there right now. But another reason why it probably doesn't have life is because it doesn't have a magnetic field anymore. Mars has no magnetic field, which means that radiation from the sun in the cosmos can strike the surface. Radiation is very deadly. X-rays, gamma rays perhaps, can strike the surface and harm the life there. So again, there are many reasons why there's probably no life on the surface of Mars, but there is life perhaps underground. Perhaps. We don't know for sure, but we're looking. We're trying to figure it out. Somebody asked, would sound travel faster? No. On Mars, sound has to propagate through a medium, right? So in our atmosphere right now, the reason why there's sound is because as I'm talking, I'm moving air, and the air has a certain frequency, right? That air is moving at a certain frequency. And those frequencies get sent through the air to other people's ears, and their ears can tingle, they can sense it, and it gets sent to the brain and you hear it as sound. A remarkable thing. But, so sound is dependent on the medium in which it is traveling through. In the oceans, sound travels faster, right? So on the surface, sound travels at about 600 miles per hour. Slower if you're going, the higher you up you are. So at this very surface, it's about 700 miles an hour, which is roughly in kilometers per hour. That's like 900, I think 900. The point is, or 1,000, maybe 1,000. The point is that the medium in which you are traveling in is how fast sound travels, right? The more molecules of air there are, the more molecules you have for that sound to travel through, the faster it's going to propagate. In the oceans, sound travels faster than in the surface. Sound travels very quickly in the oceans because there's more molecules to vibrate. There's more molecules there that can vibrate and traverse those frequencies out. But on Mars, the Martian atmosphere is very much like the tippy top of our atmosphere on Earth. Sound travels much slower there. So if you were to be on Mars, you would hear very muffled noises, very muffled, very silent. Just barely notice, like that, right? Barely notice. And it'd be muffled. It'd be like that. So there would be sound, but interestingly, it would be very, very weird sound that we're not used to. But the good news is that we could potentially terraform Mars, potentially one day. And this is far in the future, but maybe one day we can melt the ice on Mars. Maybe we can melt it, make it warmer, right? Give it an atmosphere, give it more temperature. Melt the ice, make perhaps liquid oceans. Maybe one day we can make it like Earth again. In that case, it'll be different. But the gravity of Mars is very much less than Earth. On Mars, you can jump about 2.5 times further. If you can jump 3 feet on Earth, I can jump 6, 7 feet on Mars. On Mars, you can play basketball very easily. You'll be able to jump to the hoop no matter where you are, right? On Mars, even a baby or a child could reach the net and slam dunk. Because there's less gravity, right? There's less mass, hence less gravity, which means you can jump further. Who's learning in these lives? Who's excited? Who's happy about learning these amazing things? Should we colonize other planets? Well, I think that we belong. I think that we deserve to be in other planets. We deserve to keep learning, to keep living and being out there and traveling space. I think we deserve it. But it's not easy. It's not an easy task. All right, any other questions? Who cares about Mars? We can't live good on Earth. Well, I agree. There are many problems on Earth, and a lot of people will say, "Well, why waste time in space when we have problems here?" Well, I say, why not do both? We have enough resources to do both. We can help people on Earth and go to Mars because we have enough money to do that. It's just that people don't have People, that's our problem on the earth, right? We are very greedy. We're very, very unjust here. But we could potentially do both. We don't have to sacrifice. We can do everything. But I will say that going to space helps us learn more about the Earth, right? When we went to the moon, we learned more about our place on Earth, right? For example, take a look at this photo. Earthrise, one of my favorite photos. This was a photo taken from a spacecraft on the moon. Look at it. Look at this. This is the moon's surface. And that's the Earth. That's our planet. That's the Earth from the moon. That's like how we see the moon on Earth, right? But it's the reverse. So this picture changed the way we saw Earth, right? This is 1970, 1969, 1970, 1971. That picture changed the way we see each other, right? Because now, from that picture, do you see borders? Do you see countries? Do you see religions? Do you see nationalities? No. You see one planet. One planet. One Earth. All together. One planet. So, after this time, we developed the EPA, the Environmental Protection Agency, right? People were moved by this photo on Earth. It was clear and obvious that going to the moon changed the way we see the Earth. For the first time, we had this perspective of the Earth being fragile, this fragile world. Look how thin the atmosphere is. Look how thin it is. It's a tiny layer. Look how thin it is. The Earth's atmosphere is a very thin layer. In fact, if it would only take you about an hour. The Earth's atmosphere is only 60 miles wide. That's it. After that, you get into pretty much, there's no more air there, essentially, right? All the air, all the oxygen is about 60 miles high. That's it. That's how thin the Earth's atmosphere is. And we all share it. We all share this one atmosphere. Everything you emit, all the pollution, all the garbage you spill out there, we're all breathing it in, right? So that makes you realize how fragile we are when you recognize our place in the cosmos. So going to space helps us learn about our planet here, as well as giving us challenges, right? When we went to space, we had to learn ways of living in space, and this allowed us to develop things like the microwave, right? Many inventions were produced because of the moon missions. Going to space is an endeavor that helps us on Earth, as well as give us a sense of exploration and hope for the future, right? Dreaming. We're dreaming of the future. Let's go. Let's explore. Humans, it's in our nature to explore, just like our ancestors did, right? Like I showed you before. Our ancestors explored in Africa. They left the trees. They were curious animals. That's what made them survive. That's what makes us human. Our ancestors that left the trees and were curious as to what else is out there. Willing and having the courage to change and adapt. That's what makes us human. So potentially we can go to space. That's our next frontier, right? The new frontier is going to space. The moon, Mars. Let's go. Let's go out there. Let's do it. Let's do it. Let's we're all so curious about the world. Let's figure it out. Let's learn about it. Let's look at it. The world is much bigger than you think it is, right? The world is very big. 90 billion light years across. Lots of stuff. Look at all these stars. Look at all these galaxies out there. Here's another amazing photo of the Hubble Deep Field. This is one of the first images that changed the entire world. So, this is the Hubble Deep Field. This photo was taken by the Hubble's telescope in 1995. These aren't stars. No, these are each one of these dots, entire galaxies. Each one of these dots is an entire galaxy full of hundreds of billions, perhaps even trillions of stars each, right? Think of how many stars in this one photo. There's countless in this photo. There's what? Hundreds of billions times what? Maybe 10,000 dots here? That's quadrillions of stars. Quadrillions of stars in one photo. That's remarkable. And what's even more remarkable is this. This photo was taken from a tiny patch of sky. So, imagine looking up at the night sky, right? Imagine looking up at the night sky. This is the moon, right? This is the scale of the moon, right? Just imagine looking at the sky and seeing this moon. That picture that we just saw, that amount of space was the size of this square. That's it. That's how much space that was. All of those galaxies were in that tiny fraction of that space. Mind blown, right? Look at how much space that is. That's like taking a penny up at arm's length at the sky, right? That's how much space was that photo. This photo. That's remarkable. That's amazing. Right? Look at how many stars in that one photo. There are 10 to the 26 stars in the universe. At least. That's as far much as we can see. That's how much we can see. There could be all kinds of stuff outside of what we can see. That's just the observable universe. You guys want to take a look at that? You guys want to take a look at the known universe zoom to scale? Here's the last thing I'm going to show you guys. But this is the scale of the universe. Right? This is a person. Okay, now we're traveling outside. Oops, sorry. This is California. Right, now we're zooming out. Here's California, Americas. There's our planet. That's our planet right there. The Earth, 100,000 kilometers. There's the moon, the moon's orbit. Right, now we're out in space, and out the Earth is a little dot, right? We're 100 million kilometers away. There's our sun, all the orbits of the planets, Jupiter, Saturn, Neptune, all of the planets there. There's Voyager, the one that took the pale blue dot. There is the Oort cloud, the outer solar system. The Oort cloud is right here. The most outer part of it, the heliosphere. Okay, now our sun is a tiny dot. A tiny dot. This is 1,000 light years across. 10,000 light years. And here's our galaxy. Look at that. That's where we are. That's where we are. On that one little outskirts of this galaxy. This big galaxy. Full of billions of stars. That's where we were. Right? And here's the center of our galaxy. Very bright. There's a big black hole in the center. But let's keep zooming out. There's more. This is not the whole universe. There's a lot more. Look. Now we have other galaxies around us. Right? Now each one of these dots has galaxies. Oh my gosh. Now what? Look at this. 1 billion light years across. Every one of these dots is a galaxy. Every one of these dots. Right? Every single one of these dots. It's a cosmic web of galaxies, right? This is called the cosmic web. Look at that. 10 billion light years across. And there's 9 of these. Imagine 9 of these That's how much we can see, right? Imagine 9 of these screens with each one of these dots, pixels, not even dots, pixels, being an entire galaxy, right? That's our universe. Now let's zoom back in. There we are, back to our galaxy, back to our star system, back to the Oort cloud, the outer rings of the solar system, back to the Earth. That's just amazing. Okay, we're back. Oh wait, now we're gonna go in. Oh, we're gonna go inside. Okay, we're going into the eye, the pupil. Oh, there's the retina. Okay, there's blood vessels in the eye. Oh, we got your blood cells moving through your body, giving your body oxygen. That's what your cells do. Oh, chromosomes, strands of DNA. Oh, look at this, DNA. There's your DNA. It's in your cells. And your DNA is full of molecules, right? This is a DNA molecule right here, right? It's just a big strand of molecules, polymers, peptides, nucleotides. That's what makes up your DNA. This is what makes you who you are. Each one of these molecules makes you who you are. They give rise to your genes. They give rise to your body, your physiology, your hair color, right? Your hair color is decided based on what that DNA says. All right, let's go further. Okay, now we're going to the, here's a group of atoms. Okay, here's one atom, right? Electron cloud. Remember, electrons at this point are you can't even see them individually. They're just clouds of stuff. Emptiness, the nucleus of the atom. It's the center of the atom. There's protons make up the nucleus, and quarks. Quarks. This is the smallest we'll ever see. Well, we can see as far as today. And there we go. Now we're zooming out. Amazing, right? That's the scale that we're looking at, right? And this is not even like the main thing. Or I'm sorry, this isn't even everything there is. But let's take a look at the scale of us and other planets. Oh, there's the Earth. Here's a super Earth. So outside of our solar system, there are other planets. We've found thousands of them so far. And we know that they exist around other stars. And here's one called Kepler 452b. It's actually a rocky planet just like Earth, but bigger than the Earth. This is a planet that's bigger than the Earth and rocky, and probably has an atmosphere too. Again, there's the Earth. Oh, there's Neptune. Look how big Neptune is compared to the Earth. Look, there's the Earth, there's Uranus. Here's more exoplanets, kind of like Jupiter-sized. There's Saturn. It's a big boy, right? Compared to the Earth. Look, the Earth is right there. It's a little baby. It's a little baby compared to Jupiter. Look at Jupiter. You can fit a thousand Earths in one Jupiter. That's how big Jupiter is. It's a big ball of gas. Here's the moon. If you can barely see it, there's the moon. I don't think you guys can see it, but it's a really little tiny little baby pebble compared to the Jupiter. Okay. Now that's the biggest planet in our star system. Here's a baby star. Right. This is a baby star. Now you're getting into star size. It's a very cold, likely brown dwarf. Here's a WASP, a very large planet. Probably a dead star. Oh, here's Proxima Centauri. So this is a star this is the closest star to us, Proxima Centauri. It's a red dwarf. It's not that big. It's actually not that big of a star. In fact, most stars in the galaxy are not that big. They're about the size of this. Our sun is average. It's a bit average, a little bit bigger than average, but nothing too special. So let's go back. Here's some more stars. here's our sun, right? The sun's a big boy compared to the Jupiter, compared to the Earth even, right? You can fit 1 million Earths at least in the sun. The sun is a big ball of gas. Remember, that's what the sun is, a big ball of gas and plasma, very heated, and that's what gives us energy. That's what fuels everything about our lives, everything about us. Okay, here's some other stars. Look how big these stars can get. Here's a black hole, the one that's in the center of our galaxy. More stars, Betelgeuse. Look how big these stars can be. Look at this. This blue one isn't. This blue one is about 1,000 times the size of our sun, right? And look how big these guys are. These are even bigger stars. These are gigantic ones. Oh my gosh, even bigger star. These things are massive. Some of these stars are very, very big. Just unfathomable size. So, yeah. That was a lot of information. How do we have pictures of the sun? Have you ever tried to take a picture of one? Yeah, so we have UV. We have different. If you were to take a camera at the sun, of course it's going to be blurry, right? But we have special devices. We have special spectrometers to take a look at the sun, and we can see it in different wavelengths of light, right? Filters, yeah. And that's what allows us to really see it. So here, for example, I have a book here. It's called Cosmos, a great book. Where it shows you the filters of our sun. Here's one. This is a real photo of the sun. And you can see it's very, very active, right? Lots of little spots. Right? These are fields, magnetic fields, lots of them. Plasma, corona, right? This is the sun and UV filter. Again, we can't see all the light frequencies. We can only see a little fraction of it, right? But here's an X-ray image of the sun, and now you can see other aspects of it. Now you can see the coronas. You can see the magnetic loops that come out of the sun, right? So different filters allow you to see different things. Interesting. Oh, thank you for the gifts. Appreciate that. Here's an ultraviolet image. Talk about dinosaurs and their demise. Sure. Dinosaurs. The dinosaurs died about. Well, the dinosaurs didn't actually die. Dinosaurs, most of them died, right? The asteroid impact was so big, and I'll have a picture of that. Give me 1 second. I have a lot of tabs open, but I got 32 gigs of RAM, so it's okay. This is one of my favorite simulations of asteroid impacts. This is amazing. What an amazing video this is. Okay, so here's a crater done by I believe it's like a 200-meter wide asteroid. Yeah, I'm going to get to all these questions in a second. I just want to show you the impact. The size of the impact, the size of the asteroid that wiped out the dinosaurs is about 10 kilometers wide. Right? It was about this size here. And take a look at how destructive it was. It was super destructive. Yep, it was just one big asteroid. Dong, dong, dong. There it is. So you can see here, it gets heated as it enters the atmosphere, right? A shock wave gets produced, and it smashes into the surface. Radiation, just superheated, molten, spreading outwards because of the amount of heat generated from the impact. Right? Look at that. Leaves a crater 200 kilometers wide. That's about 50, 60 miles wide. That's the devastation that it caused. Right? But what really killed the dinosaurs was not necessarily the impact. What killed the dinosaurs was the dust. The dust from the impact. Right? Think about all the dust that was emitted from the impact and went out into the atmosphere, and it blocked the sun. Right? So think of all the trees that were living at the time. They couldn't get sunlight. They died off. Right? Think of all the animals there, and look at this dust cloud surrounded the entire planet from the impact. Right? Dust. It wasn't like this. I mean, it was noticeable, but it wasn't like this. The point is that given enough coverage, the entire planet was covered in dust and it blocked the sunlight. And what this did was it made the Earth cold, about 10, 20 degrees colder. The dinosaurs, the larger ones, couldn't survive, right? Very, very few animals survived. Only about 20% of land life survived. So, again, the immediate impact was not there. It took decades for the dinosaurs to slowly die away. Right? They didn't die instantly, but it took decades for them to slowly die away. And it's pretty sad, but right, they were looking for food. The larger dinosaurs, they depended on the smaller dinosaurs to eat, but they couldn't find them. Right? They needed more food to survive. Hence, they died fastest because they needed more food than the others. That's one of the downfalls of being bigger. Right? You need more food, more energy. But the smaller animals didn't need as much energy. Hence, they could survive better. They survived underground. Right? So that's what killed the dinosaurs. Now, people ask, well, where did the asteroid go? Well, the asteroid was so hot when it hit the Earth. There was so much energy there that it vaporized on impact. It vaporized. And the asteroid hit near Mexico, near modern-day Mexico. And it was watery. There was no land at the time. It was low-lying land, if anything. But it struck Mexico. And approximately right here. So there's Mexico right there. And what happened was it hit the land, but it also hit the land. The water was so thin, so low-lying that it struck the surface. Right, the water levels on the planet are very thin. But after the impact, produced all that dust, debris. What was I gonna say? Oh yeah. So the asteroid was vaporized. It got vaporized and turned to gas and dust. But the evidence of the impact is right here in the geological strata. So if you notice, if you take a look at this layer of stuff, right? If you notice, you'll see in the rocks, right? When you take a look at the bedrock of the Earth, you'll notice that you see this white line right here. You guys see it? Do you guys see that white line? Very thick white line, right? You see it? That is a layer of iridium. And for many years, People saw that around the world because this layer exists all around the world. People saw it, they didn't really know what it was. They didn't know what it was. But in the 1970s, 1980s, geologists discovered it, and they realized that they discovered the impact near Mexico. And they realized that, wow, this iridium is likely linked to the asteroid. Because iridium is it's an element that is found in asteroids in very high amounts. So this dust, like I said before, as the dust surrounded the planet, it sunk into the soil, right? The dinosaurs as well. And all that stuff, all that ash and dust and iridium mixed in with it, it solidified and became a geological It became a geological layer. And this is called the KT boundary, or the KP boundary. And that's the evidence of the impact right there. This is it. This is proof of the dinosaurs dying. Let alone the fossils, right? Let alone the fact that we find their fossils. But yeah, that's the story. That's how it happened. It's quite remarkable, quite amazing. I actually live right near right near the impact. Really scary. Okay. Man, I'm tired. Whose mind is being blown right now? Who's like, wow, this is crazy? Who's enjoying this? This is amazing to me. I love science. It's amazing. Yeah, science is amazing, right? This is why science is my favorite. Can you explain quantum fluctuations? It's not easy to describe, but PBS Spacetime has a good video on it. Yeah, so in space, you have something called quantum fields. They permeate all of space-time, right? And these fields, they can fluctuate. It can be ups and downs of energy. On the quantum level, things happen very weird. Very, very weird. Like, you can have things existing in multiple states at one time. It's called superposition. But these fluctuations can occur. And if you have a strong enough fluctuation, you get energy yielded from the process. Energy can be yielded because a lot of the vibrations of these fields, they contain potential energy, right? So when there's enough energy to make it break, energy gets released and it turns into a universe that we know today. It turns into inflationary energy that makes the universe become bigger and larger. That's all I can really explain. That's the simplest way I can explain it. It's way more complex than that. But again, I'm not going to talk about that.